K2-18b may represent a new chapter in humanity's search for life beyond Earth. When we look into the night sky, surrounded by billions of distant stars, one question continues to capture our imagination. Are we truly alone in the universe? For centuries, that question belonged mostly to philosophers and dreamers. Today, powerful astronomical instruments are allowing scientists to investigate it with actual observations. One of the most important tools in that search is the James Webb Space Telescope, or JWST. Its powerful infrared instruments allow researchers to study light from distant worlds and search for chemical fingerprints within their atmospheres. One such world is K2-18b, a distant exoplanet located roughly 120 light-years away in the constellation Leo. It belongs to a category known as sub-Neptunes, planets larger than Earth but smaller than Neptune. This makes K2-18b particularly interesting because our own solar system does not contain a planet that fits this category. It is neither a conventional rocky Earth-like world nor a massive gas giant like Jupiter. K2-18b orbits a red dwarf star known as K2-18. Although its orbital distance is much smaller than Earth's distance from the Sun, its cooler host star changes the conditions dramatically. The planet lies within a region where temperatures could potentially allow liquid water under the right atmospheric circumstances. And that is where the scientific excitement begins. Observations of K2-18b have provided evidence for water vapor in its atmosphere. Water is an important ingredient for life as we know it, but its presence alone does not prove that a planet is inhabited. Scientists therefore examine other molecules as well. Spectroscopic observations can reveal chemical compounds by identifying the wavelengths of light they absorb. Studies of K2-18b have reported evidence for molecules such as methane and carbon dioxide, both of which can occur naturally through different planetary processes. Another molecule attracted particular attention: dimethyl sulfide, or DMS. On Earth, DMS is strongly associated with biological activity, especially marine microorganisms. Because of this connection, researchers became interested in whether a similar chemical signature might exist in the atmosphere of K2-18b. However, an important distinction must be made. A possible detection of a biosignature is not the same thing as discovering life. The reported evidence for DMS has required additional analysis and confirmation. Scientists need repeated observations and stronger statistical evidence before concluding that the molecule is genuinely present and determining whether it could have a non-biological explanation. That caution is essential because planetary atmospheres can be extremely complicated. A molecule associated with life on Earth might potentially be produced by other chemical or geological processes under different conditions. Therefore, researchers must consider the entire atmospheric environment rather than focusing on a single compound. Still, K2-18b remains scientifically fascinating because it may belong to a class of planets known as Hycean worlds. The Hycean concept describes hypothetical planets with hydrogen-rich atmospheres and substantial oceans. These worlds could have conditions dramatically different from Earth while potentially maintaining environments where certain forms of life might survive. If K2-18b is indeed a Hycean world, its atmosphere and interior could provide an entirely different pathway toward habitability. Instead of searching only for Earth-like planets with continents, oceans, and familiar atmospheres, astronomers may need to consider worlds that look completely different from our own. That changes the question. Perhaps life does not require a planet that resembles Earth in every way. Perhaps some forms of life could exist in environments hidden beneath thick atmospheres or within deep oceans on distant worlds. K2-18b does not provide a confirmed answer yet. But it has demonstrated something extremely important. The search for life can now examine the atmospheres of distant planets in remarkable detail. And the deeper scientists look, the more possibilities they discover. The story of K2-18b becomes even more fascinating when we examine the idea of Hycean worlds. The term describes a proposed class of exoplanets that could contain hydrogen-rich atmospheres above large quantities of water. These planets may be considerably larger than Earth while still potentially offering environments where liquid water could exist under particular atmospheric conditions. The concept expands the traditional definition of habitability. For decades, the search for life beyond Earth often focused on rocky planets located within the habitable zone of their stars. The basic idea was straightforward. Find a world at the right distance from its star so that liquid water could potentially exist on its surface. But planetary science has become much more complicated. A planet's atmosphere, pressure, chemical composition, internal structure, and interaction with its star can dramatically affect whether water remains liquid. Hycean worlds offer another possibility. A thick hydrogen atmosphere could trap heat and create conditions very different from those found on Earth. Beneath such an atmosphere, a planet could potentially contain an enormous ocean. That does not mean every Hycean planet is habitable. Extreme temperatures, atmospheric chemistry, pressure, and radiation could still make a world completely hostile to life. The important point is that these planets give scientists another environment to investigate. K2-18b is particularly valuable because its atmosphere can be studied using transmission spectroscopy. When the planet passes in front of its star from Earth's perspective, some of the starlight travels through the planet's atmosphere before reaching our telescopes. Different molecules absorb different wavelengths of that light. JWST can analyze those changes and identify chemical fingerprints. This technique does not produce a conventional photograph of the planet's surface. Instead, it allows astronomers to infer information about its atmosphere by studying the light passing through it. Observations of K2-18b have provided evidence for atmospheric molecules including water vapor, methane, and carbon dioxide. Researchers have also investigated possible evidence for DMS. But the possible DMS signal remains an area requiring further study. Additional observations are necessary to establish how strong the evidence is, whether the molecule is genuinely present, and whether alternative chemical explanations could produce a similar signal. This is how the scientific process works. A remarkable observation is not immediately treated as proof. Researchers test it, challenge it, collect more data, and compare it with competing explanations. That process may eventually strengthen the case for a particular interpretation, or reveal that the original signal had another explanation. Either outcome would be scientifically valuable. If future observations confirm atmospheric conditions compatible with a Hycean environment and strengthen evidence for potential biosignatures, K2-18b could become an important target in the search for extraterrestrial life. But if those signals disappear under better observations, scientists will still learn more about how atmospheres behave on distant sub-Neptune planets. And that may be the greatest significance of K2-18b. It is forcing scientists to broaden their understanding of what a potentially habitable planet can look like. The universe contains an enormous variety of worlds. Some may be rocky and Earth-like. Others may be covered by deep oceans, wrapped in thick atmospheres, or governed by chemistry unlike anything found naturally on our planet. The search for life therefore cannot rely on a single template. K2-18b may not contain life. At present, the observations do not establish that conclusion. But it demonstrates that modern telescopes can investigate the chemistry of worlds more than 100 light-years away and search for combinations of molecules that could potentially reveal biological activity. Future observations will be crucial. With additional telescope time, scientists can refine atmospheric models, improve measurements of chemical abundances, and determine whether the planet truly possesses the conditions suggested by current studies. Whatever the final answer turns out to be, K2-18b has already changed the conversation. The search for life is no longer limited to asking whether another planet looks like Earth. Now scientists can ask a much broader question. What kinds of worlds can actually support life? And somewhere among the countless planets scattered across the galaxy, the answer may be waiting in an atmosphere we have only just begun to read.